Hi guys, welcome to my YouTube channel. Today we're gonna go over Chapter 1 Biochemistry for MCAT. We're gonna use the milestone review sheets to go over the topics. It has almost all the topics. Some of the things which it doesn't have, we're gonna cover it at the end of the Chapter 1 from here. So let's begin. So, first thing is, chapter 1 is amino acids, peptides, and proteins. The first thing to know is all 20 amino acids. We'll make a new video for all 20 amino acids, how to learn it. So, make sure to check that. So, let's go over the overall structures of amino acids. So, amino acid is a molecule which has four groups. Sorry, four groups attached to it. Like I can draw. So this is like a carbon, and then one will be the acid side of it, which is C double bond OH. One will be the amine side of it, which is NH3 plus. I'm just gonna make it protonated, and then one side will be H. So these are the constant three parts of amino acid, and the fourth one is the R chain. Basically, this is the part which makes all the 20 amino acids different from each other. So let's just read. A molecule with four groups attached to a central, this is the central alpha carbon, with an amino group which is NH3 plus in a protonated form, the carboxylic group which is C double bond OOH, and hydrogen atom, and the R group. The R group, as I told, determines all the amino acid behavior. Okay, let's just erase this. Okay, next we come to the stereochemistry of it. So all all the proteins are chiral carbons except for glycine, because glycine has R group also as H. So because it has 2H, so it's not a chiral carbon. For a carbon to be chiral, it should have all four things, like the all four groups should be different. So all the proteins are chiral carbon. The alpha carbon is a chiral carbon for it, and except glycine, and all of them are L type, that is like levo, and all the carbohydrates are G configuration. All the amino acid except cysteine has S configuration. Okay, now we came to the hydrophobic and hydrophilic part of it. Amino acids with long alkyl chains are hydrophobic, because alkyl chain is like long hydrocarbon chain, just which has just multiple C bonds. So that will be hydrophobic, something like this. So this is C, and then if the R group is multiple C, and C bonds, that means it's like a hydrophobic amino acid. Hydrophilic amino acid would have something which is like more hydrophilic, like alcohol or something like that. Again. Now we came to amphoteric. So all amino acids are amphoteric. They can either act as base or as either base or acid, because they can be protonated and accept a proton, or they could be deprotonated and just give away their protons. Okay, then there's a thing called pKa, which is which is like pH value when half of the species are deprotonated and half of the species are protonated. So it looks like this. And if you see the formula, is it here? I can write it up for you guys. Okay, it's not here. So if you see this formula, which says pH is equal to pKa, B, okay. So if you see this formula where pH is equal to pKa plus log of H plus over HA, right? So when this would be equal to this, where that's what is written over here. So if these are here, the log value will be 1 and log 1 is 0, so your pH will be equal to pKa. Okay, so that's the pH. I mean, pK is the pH when these two are equal to each other. Okay, if the amino acid is fully protonated, like I drew in the starting of the video, the fully protonated amino acid, then its pH is lower than 7. 7 is the neutral pH, so pH will be lower. And if it's fully deprotonated, that means it has NH2 at one side and C double bond OO minus. That means it is deprotonated. Both the H atoms are not there. So, H protons are not there. So it will be higher pH. pH will be equal to Pi. Pi is the iso potential point or isoelectric point where the whole atom will be neutral, like it will be at pH 7, and that neutral form of an amino acid is called Zwitterian ion. Okay, so the isoelectric point is where the pH of amino acid where it is a Zwitterian ion or a neutral ion. Okay, and charges just all the charges cancel out to give, so it doesn't mean that there should not be any charge. There could be one positive and one negative, so positive and negative will just cancel each other and it will give you a zero charge. So it doesn't necessarily mean that there should be no charge, it just means that it's a neutral amino acid. Okay, and now how to calculate this isoelectric point, this is very important. So how to calculate it? So if you have neutral, sorry, just a sec. Yeah. So if you have neutral side chains, for example, you can say serine, threonine, those kind of amino acids, then you can just take the pK value, which would be given to you mostly from the COOH, and from the carboxyl side and from the amino side, add them and just divide them by 2 and you will get the isoelectric point for the neutral side chain. Okay, same when there is no side chain, for example in glycine. Okay, for the basic ones like histidine, lysine, arginine, you have to take the side chain of the R group, I mean pK of the R group or the side chain, and pK of the amino group, because it's a basic amino acid, right? It has a positive charge overall. And then for the acidic one, which is an overall negative charge on it, then you will take the carboxyl side and the R side pK, plus them and then divide. So these are the equations that you should know. Then if we go to titration, in titration the curves look like somewhat this, right? So here at the middle, here you can, it's called the equivalence point, where the pH will be equal to Pi and the amino acid will be neutral, and midpoint is like in between from start to this, so somewhere like here or here, where pH will be equal to pKa, where both the deprotonated and the protonated forms will be equal. Okay, now we came to the terminology for the peptides. Dipeptide means that it's made up of 2 amino acids. Tripeptide means it's made up of 3 amino acids. Oligopeptide means it is less than 20. So it's not like you will be asked definitions on MCAT for these kind of things. You would just be asked like it won't be asked, it would just be written in the the passages that you will get, that for example you have XYZ oligopeptide, it happens like that. So it should be like a basic information in your mind. Okay, oligopeptide means that it's a smaller protein, less than 20. Okay, polypeptide means that is more than 20, so it's a bigger protein. Okay, now how do like proteins form? So we know it's like we have a lot of amino acids. So when we combine the amino acid in different sequences, it will form a protein. So how can we like uh, put the 2 amino acids together? There should be a bond in between, right? So that bond is called a peptide bond or dehydration reaction or condensation reaction. Basically, you're taking the water away, like you can see here. So this is like the amino N terminus or the amino part of this amino acid, and then here we had the C double bond O and then OH over here. So what happened was one H was taken from this amino group, and then the OH was taken from this carboxylic group, and then there was this bond formed, which is called the peptide bond. So this bond is called the peptide bond. Okay, and this peptide bond is kind of important because this joins all the amino acid together, and you know how proteins are important, they do all the function in the body. So and you should know nucleophilic amino acid, it's like from your organic chemistry. Nucleophilic means rich in proton, so this has an additional H ion which it can give, so it's nucleophilic. And then C double bond O OH doesn't have another H plus, so it will accept it, so it will be electrophilic, that means proton loving, so it will take the H plus with it, so it will become water. OH minus plus H plus will become H2O and just gets out of here, and then this bond will be formed. Okay, and this peptide bond is a rigid bond because it has a double bond characteristic. So for example, you can see if we put like the double bond over here, then you will have a negative charge over here, right? So it has a resonance structure and a double bond character to it, so it's like a rigid bond. Okay, and now we know how to form it. To break it, we'll use hydrolysis reaction, which uses H2O. Like we will, as we removed H2O to make the bond, we will just add H2O in it, and then similarly the amino acid sequence will break into like specific amino acids. Okay, now we are coming to the protein structures. So let's do first primary and secondary. So primary is very simple. Primary is just a random sequence of amino acid, so you can put all like amino acid in any sequence, and there would be a unique sequence that will be formed, and that unique sequence will be a primary structure. Okay, so every unique sequence will have a specific function to it. Okay, so it in a way I want to tell you guys or lead you guys to a point that random amino acid sequence will make a one unique protein, and that random sequence of amino acid will give the function to that protein. So basically primary structure determines the overall function of that protein. Okay, so sometimes it's not that intuitive. Everybody thinks, okay, the way it gets folded and stuff will tell you what the function of the protein is, but basically what amino acids and what location amino acid has in a sequence, like first, second, third, what position it has, will determine the function. Okay, and it's always written from N terminus to C terminus. That's like a basic way of writing it. Then we came to the secondary structure. Secondary structure is stabilized by hydrogen bonding between the amino groups and the non-adjacent carboxyl groups. Okay, so it will be like of two types: alpha helix, which will be like a spiral kind of thing, and then it will be beta sheets, which will be like a plain sheet. So it's not like a plain sheet, it will be like one amino acid sequence on the top and one amino acid sequence on the bottom, and then they will have like hydrogen bonding in between them. So this is what makes a like beta sheet kind of a structure. So this could be like a parallel sequence, like N. Here you have N and it goes to C, and here it goes to N to C. So this is called parallel beta sheets. And if you change this, if the first one goes from N to C and the second one goes C to N, right? So this is anti-parallel beta sheets. So parallel beta sheets and anti-parallel beta sheets. Alpha helices are just, as I said, clockwise spiral that you can see. And these are stabilized by hydrogen bonding. So this is like an important thing to learn. Okay. So primary structures are made up of peptide bonds, which is kind of a covalent bond, and this is hydrogen bonding. Okay. Then we go to the tertiary or the quaternary structure. I'll come back to the denaturing later. So tertiary structure is giving a now 3D shape to your protein. So it's made up of the same type of protein. It's just like it's shaped in a 3D structure because of the hydrophobic interactions. Hydrophobic interactions or hydrophobic effect means that whichever is hydrophobic part, which it does not like water, because phobic means hating water, right? Like if you're hydrophobic, you will hate water. So same here, hydrophobic amino acids will not like the water, so it will go deep inside the 3D structure, and the hydrophilic proteins will kind of take over it and go around it. Okay, so 3D structures are made up of hydrophobic interactions. So primary structure is made up of covalent or peptide bonds, secondary is because of hydrogen bonds, and then tertiary is because of hydrophobic interactions. Okay, other interactions that could be there is like acid basic interactions, hydrogen bonding, disulfide bonds. Disulfide bonds are mostly seen in cysteine or methionine, but it's more common in cysteine. So if you see the structure of amino acid cysteine, it will if two amino acid cysteine amino acids will combine, it will make cysteine, which has a disulfide bond in it. Okay. Yeah, so what I was telling you, hydrophobic push hydrophobic R groups in the interior of the protein, which, so this is important. It came on my MCAT. So it increases the entropy of the water molecules around it and creates a negative Gibbs free energy. That means make it a spontaneous process. So basically what happens is, I'll just remove everything from the page. Just a sec. Yeah. So what really happens is over here, so whatever the hydrophobic parts are, if they're like outside, the water will like go away from it and become like bubble kind of thing. But when we put the hydrophobic parts inside, then the water can scatter more. So you know the analogy that you might have learned in your gen chemistry classes, that more disorderedness means more entropy. So basically when the hydrophobic R chains go inside, the protein itself becomes less disordered, it will become more ordered, so the entropy of the protein decreases. But because earlier when the R chains were outside, the water was going away from it and was in like how surface tension works, so it will be like in bubble kind of things. But as soon as the hydrophobic the hydrophobic archanes went inside, all the water got scattered. Like you see, if you have like some oily surface and you put water on it, it will make like round bubble kind of thing. But if you put it like up on a surface where there's no oil, nothing, it will just flow everywhere, right? Same thing happens here. So when you put the oily or the hydrophobic part of the amino acid inside, then the water just scatters everywhere and the entropy increases. Okay, and disulfide bond, as I was saying, cysteine. When two cysteine meet, molecules are oxidized, and then the thiol group just means S bond H. So thiol group will form cysteine. So cysteine will make cysteine. Okay. Fourth or quaternary structure is that multiple tertiary structures like different monomers will join together and make new protein. So for example, hemoglobin have two alphas and two betas which is joined together. So tertiary will be like only alphas together. So if two alphas coming together, it's tertiary. But with two alpha, two betas are coming, so because they're like two different kind of monomers, so it will be a quaternary structure. Okay. Coming to the denaturing part of it. So denaturing part means that when we get into the 3D structure or quaternary structure or secondary structure, so you see it's like a chain kind of thing, and then we try to order it and then increase the order. So you're kind of increasing the orderedness and decreasing the entropy. But denaturing is like a reverse process. We come from quaternary to primary. It's mostly done to analyze what amino acid sequence we have from a quaternary protein. Okay, so how we denature it is we can either increase the salinity, like we can put a lot of salt or something, or we can lower the pH putting acid or something, or we can give a lot of heat to it. So all these three things will result in denaturing of your proteins. Okay, because it will disrupt the hydrogen bonding, hydrophobic effects, and dipole interactions. So loss of 3D structure caused by heat, solute concentration. Okay. Conjugated proteins just means that you have a normal protein and that protein is covalently bonded to something, like for example some metal ion or something which gives additional function to that protein. So that's called a conjugated protein. Prosthetic group is like from the thing which is getting attached to the conjugated protein. For example, if iron in hemoglobin gets attached to the protein, so iron is the prosthetic group and then hemoglobin will become the conjugated protein. Okay, so it could be, like I said, iron is a metal ion, it could be a vitamin, it could be a lipid, carbohydrate, nucleic acid, all these kind of things. Okay, and I think it pretty much included everything that was there in the first chapter. I would recommend you to see my another video to learn all the amino acids. We'll go in detail about all the physical and the chemical properties of it. So yeah, enjoy your day. This was chapter 1, MCAT Biochemistry. Stay tuned for more such videos. Bye, have a good day.